lesson number 5, solving radical equations. This is page 13 in your note package. So we are going to be working through this unit. So we're now looking at solving radical equations. In this, we want to just kind of review the rules for solving linear equations. So if I have the linear equation -3 equals x plus 2, I want to solve for x. What I'm going to do is I'm going to isolate x by moving everything over to the other side of the equal sign. So to do that, I would have to subtract 2 from this side and from this side. And then I would get -3 minus 2 would be -5. And I would be left with x. Positive 2 minus 2 equals 0. So from that, x is equal to -5. Now, when we're solving equations, we always think of them as like a balance scale. With the equal sign indicating that everything is the same on either side, they're balanced. So what we want to ask ourselves when we're solving is that if we square each side, will it affect the equivalency of that equation? So if I take my -3 that I get from the left-hand side of the equation and I square it, and I take my x plus 2 from the right-hand side of the equation and I square that, we want to see if that's going to affect the equivalency of the equation. So -3 squared is 9, -3 times -3. And on this side, I'm going to have to FOIL, right? So I would get x squared plus 2x plus 2x plus 4. That's using FOIL. So then I would get, I want to move this 9 over. So I get x squared. I've got 2x and 2x, so plus 4x. Plus 4 minus 9. Let's scoot up here. And then I'm going to have 0 equals x squared plus 4x. 4 minus 9 gives me a -5. So now that's the new equation. Now we want to solve it. Now thinking back to our quadratics, solving this, we're going to look for the roots. So I'm going to factor this. So I have 0 equals x squared plus 4x minus 5. I'm looking for two numbers that multiply to give me -5 and add up to +4. So that would be x plus 5, x minus 1. So from that, to solve this new equation, x would equal, well, to make this equal 0, x would equal -5. To make this equal 0, x would equal 1. Okay, so that would be my solution. Now, we have two solutions, whereas in the original equation, if we scroll back, we only had x equals -5. So why do we have two solutions now? And now what we want to ask is, are they true solutions to the original equation? So we have to test this, and we test this through verifying. So we're going to test these values. So test. So I take my left side and my right side of the equation. So I'm going to test x equals -5. So here I have on my left side -3, and on the right side I have x plus 2. So if x equals -5, this stays as -3. I substituted a -5 here, plus 2. This is -3. -5 plus 2 is -3. So yes, this one works. So this is a valid solution. I'm going to do the same thing with my x equals 1. So testing here, x equals 1. So again, the left side is -3 and the right side is x plus 2. So it stays the same. 1 plus 2, -3 equals 3. Let's make that look prettier, just because I can. Well, -3 does not equal 3. So this one does not work. So this is not a solution, okay? Why does that happen? Well, there's a couple of reasons here, or things that we need to think about. What happens is by raising both sides to a power, some solutions may not work. We get an extraneous root. By squaring both sides, the -3 became positive, and the x plus 2 became a quadratic, and it was no longer a linear equation. So what happens is we get this extraneous root, and only x equals -5 is a true solution. So with these, when we're going to be doing squaring to solve, and we will be doing that with radical equations, what happens is we now have to verify our solutions. We can't just take it for granted that they will work. So we have to do that verification process where we substitute into both the left and right side to solve. Sometimes they both will work, but sometimes they don't. Okay, so your turn. So you're going to try this one. So if you can, you're going to do the trick where you press pause, you try it, and then you turn the computer back on, or turn the video back on, and see if you got it right. So press pause. And we are back. So we're going to solve the equation 5x equals 10. So if I have, oops, sorry about that, guys. I scooted my page up by accident. I have root 5x equals 10. I want to solve this, so I have to get rid of that radical. So I'm going to square both sides. So I'm doing the same thing to both sides of the equation. And when I do that, on the one side, square root of 5x squared becomes 5x. And on this side, it'll be 100. So I would get as my solution, I'm going to divide both sides by 5. It divides out on this side. And I get x is equal to 20. Now I want to verify this to see if this works. So verifying x equals 20. I have my left side and I have my right side. Now when I substitute in square root of 5 times 20 on this side, and I just have 10 on this side. So square root of 5 times 20 is 100. And square root of 100 is 10. So they work. Okay, so this does work because my left side equals my right side. Okay, now looking at the next one, hopefully you tried that as well. Does the equation square root of 5 equal -10 have a solution? And here we see some interesting things of what happens. So if we do the same work, so we square root 5x equals -10. And again, we're going to square both sides. Make sure you get that negative sign in the brackets. So we get 5x equals 100. So we would get x equals 20. But when we test this, so left side versus right side, square root of 5 times 20 equals -10. So we get square root of 100. Our -10 stays the same here. Here we're going to get 10 and a -10. Well, those do not work. So what happens is there is no solution. And the reason for that is that we can't have a negative solution when we take the square root of something, because we're always going to take the positive square root. So that we would say that this one has no solution. Okay, a little tricky there. Okay. So we're going to do some more examples. We're going to solve some equations with one radical. So we're going to solve each equation and verify the solution. So looking at here, we have our 3 root x equals 5. We want to square both sides. Okay. We're going to get 3. Oh, sorry. No. 3 squared is, my mistake. 3 squared is 9. And root x squared is x, which is equal to 25. So we would get x is equal to 25 over 9. We want to verify that. So we're going to substitute into our original equation, left side and right side. So verifying. So on the left side and the right side, I'm going to get 3 root 25 over 9. The right side is equal to 5. If I take the square root of 25 over 9, they're both perfect squares. So this would be 3 times 5 over 3 equals 5. Now if we look at this, 3 and 3 divide out. So I'm left with 5 is equal to 5. So this works. Looking at our next one, and these are easier because they only have one radical. We're going to get into more challenging ones that have more than one radical. So over here, we have 4 square root x plus 1 minus 5 equals 3. What we want to do first before we start to solve is we want to get the radical alone on its own side of the equation. So we're going to move the minus 5 over to the other side. So I'm going to get 4 square root x plus 1 is equal to 3 plus 5. So basically I just moved that 5 over, doing the opposite operation on the other side of the equation. Now once I do that, I'm going to simplify. 4 square root x plus 1 equals 8. And then I'm going to square both sides. Some people divide by 2 first. Doesn't matter which way you do it. You can divide by 2 first, or divide by 4 first, but you don't have to. So here I'm going to get 4 squared, which is 16, times x plus 1, which is equal to 64. Now I'm going to divide both sides by 16. Cancels out on this side, so I get x plus 1 equals 64 divided by 4 is 4. And then I'm going to move that 1 over, so it becomes 4 minus 1, so x equals 3. Now, if I verify them, so substituting in, I'm going to get squinchy here, sorry. I'm going to do it in blue so it sticks out. Verify left side versus right side. So I'm going to have 4 times 3 plus 1 minus 5 equals 3. So this will be 4 root 4 minus 5. 4 times root 4. Root 4 is 2, so this is 8 minus 5. Again, this is 3. 8 minus 5 equals 3, so yes, it works. Okay. Now, again, I said we want to isolate the radical first before squaring both sides. If we don't, we would have to FOIL and we would still have a radical, because if we look at this, 4x plus 1 minus 5, if we're going to square that, we have to use FOIL, right? And we would still have a radical. And we don't want to do that, okay? Now, as we move into more complicated ones, sometimes you have to actually square more than one time in order to get rid of the radical. So we're going to move ahead and see what happens. Okay, scrolling up. So what happens when we have 2 radicals? So here we have 3 root x minus 4 is equal to 2 root x plus 1. Well, before I solve this equation, what I want to do is I want to simplify it. I'm going to move all of the terms that have radicals over to one side and the numerical values over to the other side. So to do that, I'm going to have 3 root x. I'm going to move this 2 root x over by subtracting it. And then I have 1 left here, and I'm going to move this minus 4 over by adding it. Okay, so 3 root x minus 2 root x is just root x, and 1 plus 4 equals 5. Okay, now I'm going to square both sides to get rid of the radical. And when I do that, I get x is equal to 25. Again, we want to verify, so let's do our verification here. Left side versus right side. So going back to the original equation, 3 root x minus 4 is our left side. 2 root x plus 1 is our right side. We always go back to the original equation that we were given, and that's what we put in for our left and right side. Substituting in 3 root 25 minus 4, 2 root 25 plus 1. So 3 root 25, root of 25 is 5. So 3 times 5 is, we'll just write that out, minus 4. And then we have 2 times 5 plus 1. So we have 15 minus 4 and 10 plus 1. 15 minus 4 is 11. 10 plus 1 is 11. So they work. Okay. Now, this next one takes up a lot of space because it is a little more complicated. I have, in this next one, I have 2 radicals. They can't be simplified by combining. So what I have to do is I have to first foil, foil, and then I may have to square again. So let's see what happens. Now, I'm going to try and hog a lot of space. I'm going to put a line here to kind of separate that. So on the one side, I have 2 plus root 3x equals root 5x plus 4. Now, so I want to square both sides. And on the left side, I have to foil. So when I foil, I'm going to get 4 plus 2 root 3x plus 2 root 3x plus 3x. And that is equal to, well, this one's easy, 5x plus 4. Now, I'm going to combine my like terms and rearrange to solve, get to a closer place to solve. So on this side, I have 4 plus 4 root 3x plus 3x equals 5x plus 4. So I'm going to move everything except for the radical. So everything except for this term, I'm going to move over to the other side. So I'm going to leave this 4 root 3x here and move everything else over. So I'm going to get 5x minus 3x. So basically that was just moving this one over by subtracting. And then plus 4 minus 4. And the minus 4 was moving this one over. Okay. And isn't that nice? It just subtracts out. So I get 4 root 3x equals, well, 5x minus 3x is 2x. And 4 minus 4 is 0. So now I still have a radical. So what I want to do is I'm going to square both sides and get rid of that radical. So on this side, I'm going to get 16 times 3x. And here I'm going to get 4x squared. Now, I want to solve this. So what I'm going to have to do is I'm going to have to, there's a quadratic there. So I'm going to move everything over to one side. Let's simplify this first. So what do I have? 16 times 3. You know what I'm going to do first, actually? I am going to divide both sides by 4 so that I just have 4 here. I'm going to do that to make it simpler. And divide that by 4. So I'm just going to write what I'm doing so it makes sense-ish. So I get 12x equals x squared. Move everything over to one side. So 0 equals x squared minus 12x. Now from that, I'm going to get 2 possible solutions. So let's just carve out some space there. Oops, Mrs. Finley lost her page. That makes us feel like we're really in class because that happens all the time. So we're going to carve up some space. So from that, from our solutions, I would get x is equal to, well, let's factor that. I would get 0 is equal to 0 is equal to x times x minus 12. Okay, so from that, x would equal 0 or 12. And those are the two solutions that I'm going to verify. Now, putting those in, left side, right side, I'm going to squinch them in. So testing x equals 0. So we'll do that one on this side. So that'll be 2 plus root 3 times 0. And on this side, root 5 times 0 plus 4. Sorry, it's so tiny. So this will be 2. This will be root 4. So 2 and 2. So this one works. Testing the other one, left side and right side. So we're now testing x equals 12. And once again, I touched the page. Sorry about that. 2 plus 3 times 12 on the one side. And here we're going to get 5 times 12 plus 4. So we're going to get 2 plus root of 36. And this works out to square root. 5 times 12 is 60, plus 4 is 64. So 2 plus square root of 36 is 6, and this is 8. So 8 is equal to 8. So they both work. Okay. I'm going to do D, and I'll let you guys do C on your own if you want to try that out. But I'm going to do D because that'll give us enough practice here. So I'm just going to scroll it up. So C is yours to do on your own. And let's do D. So D, again, we have two radicals. So we're going to have to, we're probably going to have to square twice. So let's just start with procedure. And we're going to solve this. So I'm actually going to take root 2a equals root 5a plus 9 minus 3. I'm going to move the minus 3 over and have root 2a plus 3 equals, why did I write a 9? Mrs. Finley, her brain does weird things. So plus 3, and then 5a plus 9. It's just, for my brain, it's something easier to do. Technically, you can leave it the way it is, but this is a more complicated radical, so I kind of want to get it by itself, okay? So let's do our squaring. So on this one side, when we square, we have to FOIL. So when we FOIL, we're going to get root 2a times root 2a is 2a. And then we get plus 3 root 2a plus 3 root 2a. Those are the outer and inner. And then our last is 9. And then on this side, I'm going to get 5a plus 9. It's nice when everything on this side is under a radical and you square it, because basically all it does is take away the radical. Okay, let's simplify. Nice thing here is that I have a plus 9 on this side, a plus 9 on that side, so they will go away. I'm going to move the 2a over to the other side and combine these like terms. Okay, so 3 root 2a plus 3 root 2a is 6 root 2a, and I'm going to have 5a minus 2a on this side. So I get 6 root 2a is equal to 3a. Now here's some people, and we're going to do it this time, we're going to divide both sides by 3 just to kind of simplify it. The simpler we can get it, the better. So 3 into 6 goes twice, 3 into 3 is just once. Okay, so I'm going to have 2 root 2a equals a. Now at this point, we're going to square both sides. So we're going to square both sides to get rid of that radical. And when we do that, we get 4 times 2a equals a squared, which is 8a equals a squared. Move everything over to one side, so 0 equals a squared minus 8a. And if I factor that, we can write a little arrow up here. So 0 equals, I'm factoring here, 0 equals a bracket a minus 8. So my values for a are 0 and 8. Now, again, we're going to verify both sides. So verifying. So I have left side and right side. Let's verify 0 first. So on this one side, root 2 times 0. And on this side, 5 times 0 plus 9, and then the minus 3 is outside the radical. So this will be 0. Here, 5 times 0 is 0, so I have root 9 minus 3, so 0. This is 3 minus 3, so 0 equals 0. So that tells me that a equals 0 works, okay? And I'm going to verify the other one over on this side just because I need the space. So verifying a equals -8, or sorry, +8, my mistake. So on the left side and on the right side, we have root 2 times 8 on the left side. And on the right side, we have square root 5 times 8 plus 9 minus 3. So doing this, square root of 2 times 8 is square root of 16. Over here, I have 5 times 8, which is 40, plus 9. So this is root 49 minus 3. Well, root 16 is 4. Root 49 is 7 minus 3. So 4 is equal to 4. So they both work. Now, not all radical equations have a solution. Okay, so it's important to note that. And we kind of talked about that a little bit already. When the value of a variable determined by solving an equation does not satisfy the original equation, the value is an extraneous root. It is a root of the equation formed by squaring both sides, but is not a root of the original equation. Okay? And we know from previous knowledge you can't take the square root of a negative value. That's where we have our limitations on our variable. Also notice that in most equations, it is not indicating plus minus the root. Therefore, we're only considering the principal root. And the principal root is the positive root, okay? So this is the positive root, okay? So we are not playing games there and saying, oh, we can take the negative root. No. And we can also relate the extraneous roots to when the radicals are defined. Okay, so let's keep working on this. So let's take a look at the next page. Extraneous roots. So we're going to solve this one here. So the first thing we're going to do, square root of 2x minus 1 plus 5 equals 2. So we're going to move this 5 over to the other side by subtracting. So root 2x minus 1 is equal to 2 minus 5. So we get root 2x minus 1 equals -3. Now, we've got a radical here. We want to get rid of that radical. We're going to square both sides to do that. And when we do that, we get 2x minus 1 on this side, and we get +9 here. Now we're just going to solve for x. So 2x is equal to, we move this -1 over by adding, so it's equal to 10. So x is equal to 5. Okay, now we're going to verify this solution. We only have one. Left side, right side. So on this side, we have root 2x minus 1 plus 5, and over here we have 2. So we're just going to substitute in our value 5. So 2 times 5 minus 1 plus 9. 2 times 5 is 10. 10 minus 1 plus 5. So we get root 9 plus 5, which is 3 plus 5, or 8. So the left side does not equal the right side. So we would say that x is equal to 5 is an extraneous root. Okay. All righty. Keep going. Your turn. So again, this is your chance. If you will press pause, come back when you're done. Okay, we're back. So we want to solve this. So we have root x minus 1 is equal to root 2x plus 3. So we want to square both sides to get rid of the radicals. So we're going to get x minus 1 equals 2x plus 3. And then it's just rearranging and solving for x. So let's move all of our x's over to one side and all of our non-variable terms over to the other. So here I have negative 1. I'm going to move the 3 over. Minus 3 is equal to 2x minus x. So basically, I just move these over by doing the opposite operation on the other side. So I get negative 4 is equal to x. So that would be my solution. Now we're going to show that it has an extraneous root. So we're going to verify left side and right side. So in here, I have negative 4 minus 1. And in this one, I have 2 times negative 4 plus 3. So here I get negative 5. Already, I'm seeing problems because we cannot take the square root of a negative number. And here I have negative 8 plus 3. Now, even though they look equal, we're getting a negative value under our radical. We cannot have a negative value under the radical. So even though looking at them, you say, but Miss, it looks like they're equal. They aren't because of that negative sign. Therefore, x equals negative 4 is extraneous. It is not a valid solution. Okay? Tricky. All right, let's do the next one. Next one, we're going to look at a couple of problem-solving things using radicals. Now, don't let pictures and things like that confuse you. Just kind of go with it. Just kind of look at what information you have and solve. So we can use our knowledge to solve situations involving formulas with radicals. Recall this idea was even used in quadratic unit when we were isolating variables. Now we have this formula, d is equal to 13h, which can be used to estimate the distance of the horizon d in kilometers from an observer at a height h meters above sea level. Now, an observation platform is to be built on a fire tower. The base of the tower is 100 meters above sea level. How high must be the observation platform so that an observer's distance from the horizon is 50 kilometers? So we're going to build an observation platform here, and that means that this is 100 meters. So that's the 100 meters above sea level. This we're going to call x. So the difference from the height to the top of that is going to be x. So we want the observer's distance from the horizon is 50 kilometers. So h is equal to, from our diagram, x plus 100 meters. Okay, And D, our distance from the horizon, is 50. Now, this is 100 meters. Interesting. 50 kilometers. Okay, so D kilometers, and the height is in meters. So we're good for the fact that the units don't match because of how the formula has been given to us. So let's substitute in. So D is equal to root 13h. This is easier than you think. All you're going to do is substitute in what you know. This is why I always say make a list of what you know. And you do have to do some figuring out in terms of figuring out what h is as to where that observation platform is, etc. So D is 50, and it's root 13x plus 100. Now we want to solve for x, so we have to get rid of this radical. So we're going to square both sides. And when we do that, let's just scroll up here. We're going to get 50 squared is 2500, 2500. And here we'll get 13x plus 100. We can expand that. So 2500 equals 13x plus 1300. We're going to rearrange and solve for x. So we're going to subtract 1300 from both sides. So 2500 minus 1300 equals 13x. So we get 1200 equals 13x. We'll divide both sides by 13, and we'll get 92.31 equals x. So the tower is 92.31 meters. Now the total distance is that plus 100, right? Total distance is total height is 192.31 meters. Because if we look up here, the height is that plus 100. Okay? So that's that one. Now we have one more page, and then we're done. Oops. We're done this section. For some reason it doesn't want me to be finished. So doing a little equation. So this one says your turn. Now, whenever we see triangles, we might want to think of the Pythagorean theorem. Pythagorean theorem we use a lot in this unit. So we're looking at these two rectangles, and we've got some diagonals drawn in them, and we're going to use the Pythagorean theorem to determine these. So here it says, so again, it's your turn. So I would like you're going to press pause and then come back. Okay, we're back. So we want to determine the lengths of BD, which is this diagonal here, and HF, which is that diagonal there. So we're going to recall our Pythagorean theorem. C squared is equal to A squared plus B squared, right? So these are rectangles. So BD squared is going to equal the square of the lengths of the sides, which is 3x squared plus root 2x plus 1 squared. So basically, I'm just substituting those in for the values of the sides. So BD squared is equal to 3x plus 2x plus 1. I'm squaring those, so I can just remove those radicals. So BD squared is equal to 5x plus 1. So BD would equal square root 5x plus 1. So that's my BD. For the other one, F of H, or FH equals, and again, we substitute in the values for those sides. Sorry that it's it's cutting off a little bit. So 2x squared plus, sorry guys, there we go, root x squared. It doesn't want to stay free. So again, I'm going to square those. I get 2x plus x. So fh squared equals 3x, and f of h would equal square root 3x. Okay, so that's what it's asked us to do for the diagonals. We don't have to do anything else further after this. So now part B says, if BD is 1 unit longer than FH, determine the length of which of each rectangle. So that means that BD is equal to FH plus 1. So if I look at my value for BD, I'm going to scroll down a little bit so I can see them. That means 5x plus 1 is equal to root 3x plus 1. So I'm going to rearrange and solve for x. And I do that. So I'm going to square both sides. On the one side, I'm going to have to FOIL. So that's means a little more work, but that's okay. So here we open it up. It just becomes 5x plus 1 because squaring that radical removes that there. And on this side, I'm going to have to FOIL. So I'm going to get 3x plus root 3x plus root 3x plus 1. So I get 5x plus 1 is on this side. Here I would have 3x plus 1 plus 2 root 3x. So I'm going to move these over to the other side. So I'll get 5x minus 3x plus 1 minus 1 equals 2 root 3x. So I get 2x because 1 minus 1 equals 0. So 2 root 3x. If you want to simplify this, you can divide 2 out of both sides. Why not? And then we're going to square both sides. Okay, I do that. I get x squared equals 3x. So 0 is equal to, actually, I'm going to move everything over to the other side because I like a nice positive x squared, don't I? So I'm going to have x squared minus 3x equals 0. So I get x equals x minus 3 equals 0. So x would be 0 or 3. Now, looking in our measurements, we have f of h is equal to root 3 over x. If x were equal to 0, that would mean fh equals 0. So we're going to rule that one out, okay? So doing that, we're going to just rule that out. We're going to reject it because it's a measurement, okay? So it wants to know the length of width of each rectangle. So let's look at all of our values. So CD is equal to, we have from our diagram, 2x plus 1. If 2 is equal, or if x is equal to 3, it's square root 2 times 3 plus 1. So this is equal to 2 times 3 is 6. 6 plus 1 is 7, so root 7. Okay, and there's nothing to say we can't have a radical as our measurement. BC is equal to root 3x, so that's root 3 times 3, which is root 9, which equals to 3. GH, looking at the other rectangle, is root 2x, which is 2 times 3, which is root 6. And then finally, f of g is this just equal to root x, so that's root 3. So those are all of our dimensions, and you can go back and label the original rectangles if you want. Now, lots of practice questions, a lot of interpreting. This would be our extra practice questions. You know me, I like to put a little do-do-do-do. So hopefully that all made sense for you guys. There we go.